What's up, bitches? Today we're going to learn forced vibrations. So, what this chapter talks about is that you have a mass, spring, damper, whatever, and instead of like in free vibrations where it's just one force and then you're just computing the amplitude and the response, forced vibration talks about a system where there is a continuous excitation, harmonic excitations, defined by like an amplitude f0 times cos or sine, with a frequency and time. Okay, so you're basically applying a force like this on the system, and then you just want to evaluate the amplitude. That's basically what forced vibrations is talking about. So these are the main equations that you absolutely have to know. Unlike free vibrations, where the main equation is this plus c x dot plus k x equals 0. In this chapter, it's not equal to 0, it's equal to this, or f0 sine wt, whatever. These four equations are things that you have to know by heart. I don't know if you're going to have them in your formula sheet, but you have to know by heart for basically all of your chapters. So the way this physics class is set up is basically this is the general equation. You don't need to know this by heart, but the way you find the solution is that there's two solutions that you have to do: the homogeneous and the particular solution. And basically the total amplitude, the total response of the system is just the sum of both. All right. So what does that mean? Let's say for an undamped system, this is what's going to look. This is T, and that's your response. For an forced vibrations, undamped, zero damping, it's going to look something like this. Hold on. Some fuck ass thing like this. Okay. That's basically what you have to do. Next, if there is damping, it's going to look something like this, and then like this. This initial part here is called the transient state. It's like the initial disturbance of the system. And the other part over here, is the steady state. I don't know if you guys took the modeling simulations class, whatever. I don't know if other universities offer that, but it's very similar to that. Well, it's exactly that, actually. If it's undamped, there's no transient state. It's just steady state. It's going to look like that forever. Here, if there is damping, there's going to be an initial disturbance, and then the damping is going to like absorb the shock and make it like this initial part fade out, and like theoretically for infinity time, it's going to look like this. That's why it's called steady state, and that's it. All right, so in this chapter, if you check your lecture notes or your manual, you're gonna get like probably like 10 fucking equations. These are the main equations for the chapter that you can use. Okay, if the system has no damping, this would over here would be your homogeneous solution, and this your particular solution. Okay, just to remind you guys, homogeneous solution is just a fancy way of saying that this equation over here is equal to 0. Your particular solution is the same shit. It's just saying that it's equal to force, well, the amplitude of the force times cos or sine. That, basically. This over here basically means this. That's it. All right? So, this equation over here, I took it straight out of my, what do you call it, the formula sheet. I don't know if you have that in your formula sheet, but it's the main equation for undamped systems only, okay? This is the initial displacement. V0 is your initial velocity. If there is no, if like the problem does not specify initial conditions, you could just assume these are 0, and these two parts over here go away. F0 is the amplitude of the force, K is the stiffness of your spring, M is the mass. This omega over here, it's not omega n nor it's omega d. What it's talking about over here is the frequency of the force that's being applied. All right? If it's the omega d, it's talking about the damped response of the system. If there's nothing, it's talking about this omega over here, the force's frequency, okay? Then you have the natural frequency here, natural frequency there, and this is the same thing, all right? If your system has damping, this would be your total solution. This over here is your homogeneous solution, which is from your previous chapter with free vibrations. And this is your particular solution. Delta T is just a fancy way of saying F0 over K. They just do it like that because it looks cleaner. R is the ratio between the frequency of the force that's applying, that's harmonically exciting your system, divided by the natural frequency of your system. This phi over here is called the phase lag. It's in degrees, all right? So if you have your force over here, for example, and it looks something like this, if there is damping, your system is going to look something more like this, all right? There's going to be a little lag, and that difference is called phi. If there is no damping, this phase lag is negligible. You don't need to worry about it. But in the particular solution of a damping system, you have to take this into consideration. I'm not sure if this is going to be in your formula sheet, but if it's not, you should know this by heart because it's like the main equation for the chapter. I even included it here because a lot of the problems when they're talking about a system that has damping, almost all of them ask for the steady state response, the particular solution, because the homogeneous part is from your previous chapter. So when you're dealing with in this chapter, forced vibrations, a bunch of the problems are just going to ask for the particular solution. Now, normally in my other videos, I would just leave it at that and move on to examples, but this chapter is really fucking complicated. So I'm just going to go over how these equations were derived, just so maybe y'all can understand a little better. For your homogeneous solution, it's basically this. It's from your previous chapter. However, unlike in your previous chapter, just keep in mind that this isn't the full solution, okay? The full solution is xh plus xp. All right? So you can't just take this and use your initial values to solve for A and B because it's not the total solution, so you can't really do that. But you can use this if the, the damping ratio, if it's undamped or underdamped. All right? Now, theoretically, if your system is critically damped or overdamped, you would have to use these equations. But in this chapter, I literally never saw these, so you don't need to worry about these equations. Okay, one last thing. In this chapter, you're going to see in your manual or your lectures or your homework problems, whatever, these equations as well. These are just fancier ways to write this. Personally, I only use this equation over here because I'm most familiar with this and it's like the easiest to understand. This equation over here basically combines both cos and sine with this, okay? Unlike earlier that I said with the damped system, this isn't the phase lag. It's just a mathematical way to set the initial values, the initial conditions, all right? If you like using this, you can. You're going to get the same answer, but personally, I said fuck that. I don't like using this equation because it just makes a lot of them more complicated. Especially this fucking equation. This I don't understand how the fuck they use this for the homogeneous solution. For the particular solution, this makes more sense. I'll get to that later. But personally, I just use this and I got the correct answer. So you could use. These are just different ways of saying the same shit. You could use it. You could use whichever equation you like, whatever makes you feel more comfortable. Alright, so the main part of this chapter is your particular solution. You're going to get two cases. Either there's no damping or underdamped. For your particular solution, your steady state, you're never going to get a critically damped or underdamped, or sorry, overdamped, because then there's no vibration and you just don't need to worry about it. If there is no damping, C is just equal to 0, and this is your general equation. And they basically set x of p, which is your particular solution, as this. And then I don't know if you guys remember from your modeling classes, but you just have to take the derivatives and then plug it into here, and then it just becomes an algebra problem. So they take the first and second derivative, and then they just plug it into the equation. So they take the first and second derivative over here, and then they just plug it into the main equation. This is your main equation. They just plug in x of t over here, and then the normal x over here, right? So you get this. They just replace the values, okay? Next, they basically factorize out this part over here, right? Well, they factorize out the omega squared for here for now. So they just remove this. Next, you're left with this. So this, if you realize, is just equals to your particular solution. So they replace it with x of p over here, factorize that over here, and then they just solve for x of p. That's it, super easy. So your total solution is your homogeneous solution, which I explained a little earlier, and then this over here, your particular solution. They just switched out the k over here because it looks cleaner. That's it, super easy. Now, I don't know if you guys are going to get this in your problems, but in my formula sheet, they just wrote this. They didn't write any of this. And this is just a fancier way of writing all of this, all right? They're just taking into consideration the initial values. If they're equal to 0, it just reduces back to this. Also, some of my solutions, they use this form over here. What they basically did is they took delta, which is equal to the force divided by k, and the ratio of the frequency of the force divided by the natural frequency of the system. I guess it's just a cleaner way of writing. I didn't really use this fucking shit, but this is basically what it means. It's just a fancier way of writing this. All right, so that's if you have no damping. If you do have damping, well, you're pretty much fucked. You have the C over here, which makes it a lot harder to solve the problem. All right. So first things first, your particular solution is equal to this. All right, it's equal to some amplitude times a trigonometric value cos. This cos over here has to match with the force, whatever you're defining your force with. Okay, so if you have f0 of sine, this changes to sine. That's the frequency of the force time, and there's also a phase lag that you have to take into consideration. All right, that I explained earlier. So the way they solved this problem is they used complex numbers. So instead, they define it with these two equations over here. They basically, well, mathematically, they mean the same thing. It's just a little more simpler to solve them, okay? And the rest just becomes an algebra problem. So again, they take x of p, they find the first and second derivative, and then they plug it into the general equation over here, all right? So over here, they just picked up the first, second, and 0th derivative. They just replace the numbers over here for now. And then they factorize your e to the power of I, w, but whatever. They just factorize this out, okay? So you're left with this. Basically then, they separate these two values over here, right? So if you distribute the I, you get this, which is equal to this, right? Therefore, you're able to eliminate this from both sides, all right? So you're left with this. And then you basically divide both sides with this part over here, and you're left with this. Now, at this point, I think I took this, what was it, differential equations? I think I took that class in literally my first semester, and I took this like a year before graduating. So I don't remember exactly what's the steps, but from what I remember, this basically means this, right? This is in your, in your complex plane, right? I and real numbers. Basically means this. It's a circle, well, it's a point with radius x, and the angle is phi. It's just in polar coordinates. That's what it means, all right? So you're basically trying to solve for this. Basically, you have to see this more of like a geometric problem, I guess. To find the radius is just a magnitude, okay? Taking the magnitude for the numerator and the denominator, f0 is just f0, it doesn't change anything. For this part, the denominator, you have to take into consideration that in complex number format, they basically write it like this, okay? So to take the magnitude, it's just the, what's it called, the Pythagoras theorem. So they take this, where b, it's like multiplied by I. This is your b, and this, you consider it your a, all right? And to find the angle, it's just, again, trigonometry. You take the b divided by a, and the tangent of your phi is equal to that, right? So they're considering b as c omega because it's multiplied by I. That goes on top, this goes on the bottom, all right? So this is what we're left with. We left off over here, right? So we define the magnitude of x as this. We would take the not the Pythagoras, fuck the, what's it called? Hypotenuse, whatever. And then we find x, which is this, okay? For the rest over here, it's not that they ignored it, it's just whatever the real part of these equations is what's happening physically. They're not really ignoring I, the complex number, it's just used to mathematically solve it a little easier, right? So remember that we defined the particular solution as this. Here we found the x. So we just replace it with this, and you're left with this, all right? And the phi here is defined by this part over here, okay? That's where this equation comes from. Now, in a lot of your problems, they're going to write it like this because it looks cleaner. They basically use these equations over here to simplify this big-ass equation over here so it looks cleaner, okay? Again, R, well, I explained this earlier. R is the ratio between the frequency of the force divided by natural frequency. This, they just take F divided by K. And keep in mind that sometimes for C, you'd have to change it with this. This equation over here was not in my formula sheet. It's something that you have to know by heart. You'll probably learn it in your labs. And also the phase lag. In a lot of the problems in my lectures, they define it as this. It's the exact same thing as this. They just use this equation over here and replaced all the values to find this. But they basically mean the same thing. And yeah, that's it. All right, and that is how they found these equations. Now, you don't need to know everything step by step. Well, I hope you don't need to know. I just wanted to show you guys, just so you understand a little better how these equations like work and what they are and what they mean. Because this chapter, it gets really fucking complicated. So if you understood that, good for you. If you don't, you at least really need to understand how to use these equations in your homework problems. But that's basically what they mean, and that's it. Okay, one last thing that I forgot to mention is resonance, okay? What resonance mean is typically it happens in the steady state, okay? So this part here is transient state. Resonance happens in the steady state. What it means is basically R equals 1. Either that or phi equals 90 degrees, but like almost all of the time you just have to worry about R, okay? Resonance means that the force, the harmonic force that's being applied on the mass is equal to the natural frequency of the system. That's basically what it means. Like, you know, in movies when there's like a fucking opera singer and they want to break the wine cups, the glass wine cups, so they sing really high and then the cups breaks. That's basically resonance. That's what they're talking about. Whenever they mention that in your problem statements, which they will, it's just that you have to replace R by 1. And there's also a very good chance that in your labs in this class you're going to deal with resonance. Whenever you're measuring the device and you're applying the force at resonance, it's going to spike up really like a lot. I don't think it's, no, in a damping system it's not maximum, but it's going to be really high. It's going to go like something like fucking, it's going to go like this. That's because it's at resonance. It's typically referred to like the maximum amplitude for when there's no damping involved over here. But when there is damping, it's not at maximum. But like 99% of the time when they're talking about resonance, you just have to worry about R equals 1. That's it. All right, and that is the first half of this chapter. The next half are these unbalanced rotors and accelerometers, whatever. But basically, to find their equations, those equations, they use the general equations that I explained earlier. But I'm not gonna fucking do that because you really don't need to understand any of that shit. You just need to understand what these equations mean, okay? An unbalanced rotor, usually, it's just a disc that's rotating and they install a mass off-centered, all right? And as the whole thing rotates, this mass that's off-centered causes the whole thing to shake. That goes up and down, all right? That's it. So the big M over here is the mass of whatever is moving, okay? So sometimes you have to add the mass of you add the mass of the disk and the part over here. Sometimes, okay, it depends of the problem. Sometimes they give the total mass. Just pay attention to what the problem states. X is the amplitude in meters of how much this part is going up and down. The little m is the mass of the part they put over here. And E is the eccentricity, how off-centered it is, measured in meters. All right, so in your problem, wherever you see eccentricity in your problem statement, you should automatically think of these two equations. Sometimes they define the eccentricity as this, all right? Kg times m. Basically, kg is the mass, and that is your eccentricity. It's just me, so you don't need to add anything over here. You just plug that number here, if they define it like this. R is this. It is the ratio between the frequency of how fast this disk is moving divided by the natural frequency of the system, which is square root of k divided by big M. And that's just your damping ratio. Sometimes they use this equation as well. It basically means the same thing. They just switched out the zeta to this, and instead of using R, they're using this, but it basically means the same thing. It just depends how they define the problem and what values they give you. Sometimes this is more convenient. Personally, I always found this more convenient, but it just depends what you're comfortable with. All right, so basic excitation and transmissibility, it's what you see in the photo. There's basically a mass that's moving to some amplitude x, and it's attached to a base, and the movement of the mass is causing the base to move to some amplitude y. And the ratio between these two is t, the transmitted amplitude or force. So in your problem statement, whenever they use these words, base excitation or how much force is transmitted, whatever, you have to use this equation over here. In this equation, R means the frequency of the system, how much the system is vibrating, how much it's moving, divided by the natural frequency of the system. Also, one last thing, there's a lot of problems for some reason that use like planes that go on a runway, and the runway looks something like this, and they define the runway as y0 times cos or sine omega t, just because it looks like the same shape geometrically. A lot of these problems, they use this equation because they define the y0, the amplitude of the road, basically as y, and the waviness as the frequency. So if you see this in your exam or your problem statement, there's a very good chance that you have to use this equation over here. All right, so last thing is your accelerometer, okay? Whenever you see this word, accelerometer, or when they're talking about measuring a device, or they're measuring the vibration of a device, whatever, you have to use this equation. Z is what the measuring device or accelerometer outputs, what it indicates. It's basically the relative amplitude between the mass and like the frame. Y is the frequency of the mass that's being measured. R over here is a little different. It basically means the same thing, but here the natural frequency, you're taking the natural frequency of the device that's using to measure. Usually they're going to give it in your problem statement. And this is the frequency that's like being measured. And yeah, that's it. All right, so that's everything in this chapter. It's a lot of fuck-ass equations, but I explained to you guys everything, and I'm sure that you'll be able to solve this exercise. I took this from one of my tutorials, and the reason why I took something so complicated is because this was literally in my final exam. So pay attention, retards. Basically, it's talking about a measuring device instrument on some rubber pads on a base, and as the base vibrates, the fucking table is also vibrating, and they want to isolate it, okay? Now, basically you have to read the whole question in any exam, okay? So it's saying, in order to limit the acceleration transmitted to the instrument, it's proposed to isolate the instrument, blah, 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 okay? So I know they're using instrument, but it doesn't matter. They're not really like using this machine to measure anything in this context. What they're talking about is the acceleration that's being transmitted and they want to isolate it, okay? So immediately, our brain should go to this equation. All right, and that's it. Equals x over y. We just have to plug in these numbers and find the ratio, okay? So in the problem, they're giving us the mass of the box, 100 kilograms, and it's telling us how much it's moving up and down to 0.2 meters per second squared. So this isn't really the amplitude because it's not in meters. The 0.2 is the amplitude, like it's the second derivative of the amplitude, okay? Because it's the acceleration. And they're giving us this graph of how much the table is moving based on how much this box is vibrating, okay? By the way, this is exactly copy-pasted how the tutorial put this problem, okay? So they're giving us a hint that we have to select one of the excitations, whatever. We're going to pick up the largest acceleration because that's the most significant one, right? So y prime prime equals to 1. And it's saying that they want to use a certain number of rubber pads so that the machine peaks at 0.2. So we're going to put this as 0.2. So here we can consider that x divided by y is the same ratio as the 2's acceleration, okay? So we could say that it's equal to 0.2 divided by 1 equals 0.2. All right, so 0.2. Also, it's giving us the damping ratio somewhere over here. Where is it? Am I fucking blind? Where is it? Ah, over there. All right, so that's our zeta. It's equal to 1 plus 2 times 0.1 r squared 1 minus r squared plus 2. I'm just going to write 0.2 r squared. And now this is just an algebra problem. We have to find for r. I'm just going to do it really quick. But basically, it's saying that this value should not exceed 0.2. All right. So we're going to square both sides, 0.04. All right. I'm going to I'm going to multiply both sides with this. So that's going to give us all right, then what's the word? Fuck. I'm gonna expand this over here. All right, then I'm gonna distribute the 0.4 all the way over here. All right, next, I'm gonna send everything to the left side. Okay. Now, the rest is just basic algebra. You have to take, I'm gonna replace with this and use the quadratic formula. So you're gonna get something like this, 1184x negative 0.96 equals 0. Then you use the quadratic formula. I'm not going to write it all out, but basically, if you do this correctly, hopefully, you get x1 and x2 as this, and then this is negative 3.638. However, we want to find r, which is equal to the square root of x that we defined. So this doesn't make any sense. You could just ignore this. So here, r is equal to, actually you don't need, r is equal to plus or minus 2.569. We're going to take the positive value of this, and that's our r. 2.569 equals to omega over the natural frequency of the system. All right. The natural frequency of the system is square root of k over m. We have m, it's already given. We just have to find the k for the rubber pads. Okay, so omega n is equal to omega divided by 2.569. All right, and the omega that we chose was over here, 15 hertz. However, omega is in radians. So k over m is equal to convert it to radians is, you just multiply it by 2 pi, 2.569. Okay, and that should give you about 36.3. Next, we're gonna square both sides to get 1317.69. Nice. And then multiplying both sides by 100, we're gonna finally get 131769 newtons per meter. All right. Now the problem is saying that each rubber pads is equal to 250 newtons per millimeter. So I'm gonna divide this by 1,000 to get 131.769 newtons per millimeter. And we know that one rubber pad is equal to 250 newtons per millimeter. All right. So it's saying that it wants to limit it. Okay, now just be careful. Hello? Yeah, just be careful. It's saying that it shouldn't exceed 0.2, right? So, well, damn, to be honest, I kind of lost track. But I know that R has to be smaller than this. Not R, sorry, the K. R has to be smaller than this, because if it's any larger, then it would exceed 0.2. All right, so basically 250 is too much. One rubber pad is too much. So what this is saying is that you're going to install, hold on. Damn, I can't. What's saying is you're going to install rubber pads and they have a stiffness. And if you stack them on top, it's going to look like this. It springs in series. So not the resistance. K total of springs in series is equal to this. All right. So since 250 is too much, let's see what happens if we stack two rubber pads. What was it? 2 times 250 negative 1. Then you would get a total K of about like 125 newtons per millimeters, which is smaller than this. And that is your final answer. All right. So it's basically just, well, honestly, it's just algebra. But the hardest part in this class is really understanding what the fuck is going on, because you have like 10 equations per chapter. But as long as you really understand what these equations mean and how to use them, what each values mean, the problems become easy and it just becomes an algebra problem. And yeah, that's it.